Anybody have any thoughts about anything? Assignments? Material? Enthusiasm? I don't think that sounds something we should deal with, or is just something outside? How am I doing? Oh, thanks. The last couple of days I've been more sick. I just stayed in bed. I come up here to talk to you, but my doctor got a lot of blood work done, so we'll see. Maybe something. Thanks. So we were talking about assertions. Assertions are, yeah.
Let's say you're climbing steps,
Uh-huh.
and let's say I only take 1 or 2 steps, then how would you like start an approach if you wanted to find out like how many the number of ways it takes uh, like like
We're going to be talking a lot about this today. So why don't you hold your question until the end of the day? All right, that kind of thing is exactly what we're going to be doing. All right, so assertion is a spot in your code. You put a statement that's either true or false. And if it's true, and it needs to be true, no matter how you got to the spot, right? And if it's false, then that means your program's going wrong. And people get frightened by them because they all took 1090, which filled them with fear. All right. And I'm saying don't be filled with fear, because you can make the statement in a number of different ways. You can make it as an English sort of chat. You can make it as a picture. You can make it as a formal math statement. And in fact, I find if you do it in lots of different ways, then your audience is going to be happy because they can read it in lots of different ways. All right? All right, so what are we trying to prove in correctness? We want to prove that, well, precondition is an assertion at the very beginning of your program that's asserting what's going to be true about your input. And if when you first get in, the statement's false, then something's gone wrong, because we're only promising that this is going to work if the precondition is true. And then code. Now code I didn't put in green because it's not an assertion, right? It's the fact that you did the code. I don't know, in 3101 at least, we talk about how to turn code into statements of mathematics, but I don't think we do that here. All right, so then the last line of your code is the postcondition, right? Or at least just as you're returning, and it needs to be what needs to be true about the end, right? And so, well, what does this logic statement say? It says if your input meets the precondition and you execute the code, then the postcondition needs to be true when you leave, right? Everybody agree with this? And if you might remember from logic, if the precondition is not true, then it doesn't matter. This statement is true no matter what you do, right? All right, so here's some code, and we're going to work on on proving that it does what we want it to do. Now, of course, this is kind of hand wavy because I'm not even writing in here what we're trying to do. But what we're trying to say is that if you get to the assertion 0 and it's true, I don't care how you got there, if you got there and it's true, then when you get to assertion R, it should be true, right? Everybody good? So how are we going to do this? Oh, and of course, I think we're going to get to that. There are lots of paths through this, right? If you can see, there's two choices for the first if then else, two choices for the next, right? So the number of paths through this is 2 to the R. In fact, I probably should have updated these slides because they've gotten better in the 3101 world. Maybe I'll update them. All right. So let's think about how we might prove this. Well, we've inserted these other assertions. So let's just, instead of looking at all paths, let's just see how we get from assertion 0 to assertion 1, right? So what we might want to first prove is that this first match statement up here. And what does it say? It says, if I'm at assertion 0 and I execute the code, then I need to get assertion 1 to be true, right? And you might remember proof by cases, right? The case 1 is that condition 1 is true. In case 2 is that it's not true, right? And we know one of the other cases is, right, either it's true or it's not true in Boolean logic. So those are the only two cases, right? And so here we're doing those two cases. So in the first one, we say if we're at assertion 0 and condition 1 happens to be true, and then we execute this code, then it follows, right? You could do some mathematical logic, or you could just think about it. If this is true and this is true, then yeah, this is going to be true, right? You can write it in English. Everybody kind of see that? You see, this is a very short little proof, kind of checking this piece of code, that this piece of code gets us from assertion 0 is true and condition 1 is true. It gets us to condition assertion 1 is true, right? And similarly, here we're saying if assertion 0 is true and condition 1 is not true, right? Then we execute the second piece of code, right? And we have to show that the second piece of code then gives me assertion 1. All right, everybody good? So those are only 2 steps. Why? Because they're 2 paths from here to here, as opposed to doing all 2 to the R paths, right? And so we do each of those, right? So here's concrete example, right? We want to say, right, how do we get assertion 0 true? Right? Here you can just sort of think, all right, suppose I have 3 numbers and I set m equal to a, then m is the maximum in the set A, right? No one's going to argue with that, right? And then what's the next step? Well, we say if m is the maximum A and b is bigger than m, and we set m to be b, then we know that m is the biggest in the set A and B, right? Versus the other case, if m is smaller than or equal to b, then what do? We leave A alone. A is still A, right? Not A, m is still A. So m is the biggest. Everybody follow that? And then we can do those steps. And right, in this one, it's pretty straightforward. M is the max. We returned M, hence we return the max. Right? Everybody can see this? Breaking it down into these little pieces makes the proof easier. Right? All right. Now, loop invariance is the same type of assertion, except it happens at the beginning of a loop. And you could put it in various places within your loop, I suppose, but the classic place to put it is at the top. All right. So, and a classic type of algorithm is we get rid of this little thing. We hope it goes away, right? A lot of programs, in fact, you might have heard the word an iterative algorithm. What is an iterative algorithm? It's one that iterates. And an iteration is a loop. You do something over and over again, right? So what does this program look like is you have some sort of data structure and you store, and that's what this course is, right? And you store your present, everything you know, you store your current state in this data structure. And then each iteration, what you have to do is make one step towards where you're going, right? And just by making a simple change, because you don't want to worry about everything at all at once, right? You just do one day at a time. Everybody good? All right, so this code here has a loop in it. And in fact, remember our last code where we took the max of a bigger and bigger set, right? We're just taking that exact code and putting it in a loop, right? So, right, so what is it's just like we've been saying here, loop invariant is the assumption that's true at the top of the loop every time you're at the top of the loop, right? And what is it, and when are you at the top of the loop? Well, you're at the top of the loop when you first get there, right? After 0 iterations, after 1, 2, 3. And you're also there when you exit the loop, right? Because you go to the top and then you exit, right? So you're there. And I tend to say exit when instead of while, because I think it's easier to understand the code. But, all right, so there's our loop invariant, right? In fact, if I was going to describe how do you find the maximum of a set of numbers, you can imagine me starting with the loop invariant, right? We're going to have a loop, and when we're at the top of the loop, our kind of measure of progress is some number I, and we've considered the first I numbers, and M is going to be the maximum of those, right? Everybody say that. I mean, I've given you an awful lot about the algorithm there, right? So, right, so then, and this says, don't do all this math stuff to please the marker after the fact, right? Really, the way you should be doing it is when you're first coming up with an algorithm, come up with the loop invariant first, right? And then when you're designing the code, you're thinking about, am I getting from each assertion to each next assertion, right? When you're writing code, you have very little bits here, then it's not hard to write code in between, right? And I think I might have said this before, and it's completely made up because I'm not an expert here, but it wouldn't surprise me if you gave ChatGPT 2 assertions, it could fill the code in between, right? So it could be what your job in the future will be is designing these assertions for a bigger program, right? Hopefully that's what you'll be doing as opposed to being at home watching cat videos. All right. So my point is, let's first focus on the assertions, right? And not on the code. All right, so again, here's our code, and we want to know the definition of correctness. Definition of correctness is if the precondition is true and you execute the code somehow, no matter what the conditions are, then you'll get the postcondition, right? And do we know how many times you're going to go around? You just don't, right? All right, how is this proved? Well, we don't know how many times we'll go around. All right, so let's kind of do proof by example here. Again, all we're going to do is one assertion at a time, right? You imagine putting sort of stop spots at each assertion, right? The code runs to the next assertion. Okay, I got this assertion. Now I got to get the code to run to the next assertion, right? So here I'm at the top, which is the precondition of the problem. I got a bunch of numbers. And I have to design some code. That's the code there before the loop. That's going to establish the loop invariant, right? And my favorite number is 0. So I could be establishing that I've considered no numbers, and then I have to think, well, what's the maximum of the empty set, right? That gets a little confusing. So to avoid that, let's have our number be 1, right? I said I equals 1. I set m to be that value. And then everybody agree we've established the loop invariant, right? Everybody see that? Because we have one number, we've considered one number, and m's the maximum of those. So I call this establishing the loop invariant, right? And then we have to worry about taking a step. Now, we could think about it as we've got one number and now we want 2. Or you could leap and say, we have all we know is that we're at the top of the loop. We have no idea how we got here, right? We have no idea how many numbers we've seen, or did we do something weird in the past, right? All I know is that I have some value of n, m, and some value of I, and m is the maximum of the first I, right? And I need to make progress. So what is my measure of progress? But it's I, right? So if I increase I by 1, then bang, I've made progress, right? So in fact, let me tell you something here is that students get into a panic. How do I make progress while maintaining the loop invariant? And certainly in 3101, I say, well, first, make the progress by increasing I by 1, right? You're sort of doing that. But then you fell off the path, right? The loop invariant's not true anymore. So now you have to get back on the path, right? So how do we get back on the path? Well, after making I bigger, well, we have to consider, right? This now is our new value of I, right? Right, because we've changed I. So now we have to compare m to our new value of I, right? Everybody see how we're maintaining the loop invariant, right? And and I have a little extra statement here, like we did before, is when we're doing that, I'm assuming that we're not exiting. Why do I assume we're not exiting? Because I want to assume that there is a next value. Because if there's not a next value, we're crashed, right? So here I'm assuming we're somewhere in the middle of the code. There's still more numbers to come. I look at the next number, we maintain our loop invariant, right? Everybody good? And you'll see here, this is loop invariant is true after some t iterations versus t plus 1 iterations, right? So this is called maintaining the loop invariant, right? So we could do this when we, for our first step, and then our second step, we could keep proving this, right? Anybody idea how often I need to prove this math statement? We got a 1 here. What were you going to say? No. No, I like his answer better. All right, so let me tell you the problems with until the post condition is met. Well, first off, the post condition might be that I've returned something and I don't return anything there. So the post condition will never be met, right? So maybe you could roll it back to saying until the exit condition is true, right? I like that a little bit better. But even then, you're kind of talking about runtime, right? If I'm running it, I have to keep proving until I exit. But we're proving this during compile time, right? We're not running it. We're proving that it works on every input. So those are the problems with what you're saying. And so we don't know how many times they're going to go around, right? But the joy, why do we only have to do it once? It's just exactly, it's general, right? You make it generic enough that I'm saying no matter how the loop invariant, it's true for some reason, don't know how many times I've gone around, and I can always make the one step further, right? And we do this, we're going to use induction in there somewhere, right? Remember, induction is if you can prove it's true for 0, and you can prove that for every I, if you can get from I to I plus 1, then you can do it forever, right? So that's what we're going to use by induction. We then are going to prove that this maintains the loop invariant forever, right? But not completely forever, because it only maintains it as long as the exit condition's not true, right? But the good news is when the exit condition's not true, we will drop out, right, of the loop. Now, when we drop out of the loop, we're going to know 2 things are true, right? We're going to know the loop invariant is true. Why? Because we maintained it. And we're going to know that the exit condition is true. Why? Because we exited, right? And then we're going to know that we execute this little code at the end of the loop. Why? Because that's the next code. So now we need to mathematically prove that if we know those 3 things, then we get the post condition.
At once, because you're going step by step, like we don't know how many steps, so we'll just go to the next one.
It's always, we want it to always be true when you're at the top of the loop. Always, right? Now, when at the end, you'll go up there, it's true, you look at your exit condition is true, so you exit, right? But when you were there, it was true, right? So let's just wrap up here. If I know that m is the maximum of the first I, right? And I know that I equals n, because my exit condition, that tells me that m is the maximum of the first n, which is all of them. And my post condition says that value is returned. Oh, look it, I returned it, right? Everybody see here, you didn't have to do any weird math. All we have to do is to argue that if the loop invariant's true and your exit conditions is true, then you get your post condition, right? So these these things together prove, we like to say that they prove that your program works, but they don't quite. They prove that if your program exits, then it gives you the right answer, right? Now, you also have to prove that it exits. How do you prove that it exits? Well, I start off with I equals 1. I keeps going up every iteration. If I get to n, I'll exit. Someday I'm going to exit, right? So that gives you that you'll exit. Any questions? Are people following this? If you really are following this, then that's great, because 3101 will be easy. All right? Right? So we've sort of, did we talk about this already? It's like your job isn't worry about the whole race. You have to get the baton and go around once, right? So you establish the loop. When you first go in, you have to say from the precondition and the code, I get the loop invariant, right? And then you have to say from the loop invariant and the exit condition and the code, I get the loop invariant, right? And then you have to say from the loop invariant and the exit condition true, you get the post condition, right? Everybody buy that? All right. All right, so we're going to do some more. So let me tell you what happens in my 3101 class. Maybe it doesn't happen anymore because I give this speech, but it used to happen. People on the test would say, I'm panicking, I don't know. I haven't proved that the algorithm works. I don't understand the algorithm. The algorithm's very confusing. And I say to them, we're whispering during the test. I said, have you done the steps? Yes. All right, you've established the loop invariant, you maintain the loop invariant, you got the post condition from it, right? And they said, yes. You prove that it exits, you know the running time, and they say, yes. I said, then go home, right? Go home. And they panic because they don't feel that they've done it all, right? And so what they're lacking is the conviction of this religion, all right? So we're going to try to convince you of the religion, and then every time that you do an algorithm, you won't have to re-panic about this part, right? Right, so what is this first picture says? The little house is home, it's the precondition, and the green space, if you're on a green space, then the loop invariant's true, right? And the little yellow guy is our algorithm. And so what does that say? Can I establish the loop invariant from the precondition, right? Or suppose you can. What's the second one say? Can I get from loop invariant to loop invariant, right? If I'm off and the loop invariant's not true, then my code's going to be upset, right? But if I'm at the top of the loop and the loop invariant's true, can I maintain it, right? All right, so between these two, do you get that the loop invariant is true forever? Right? What's the name of the principle? No. How do we prove? Right? This says you can sort of establish the fact that it's true at time 0. It says you can go from I to I plus 1. Yes. Induction, right? Induction. Everybody got this? S of 0 says my loop invariant is going to be true when I first get it after having iterated 0 times, right? This statement says you give me the parsing here is a little bad. I don't know where I got this from. This says for every I, you've proved that if you know S of I, you know S of I plus 1. Right. So I would put the brackets around this thing. All right. Everybody good? Why are we doing this idea of Mars? You know, people complain to me, I don't really understand what you mean by coming in from Mars. And what I mean by it is you just dropped at the top of your loop. You know your loop invariant's true, but you know nothing other than the fact that it's true. You don't know how you got here. You don't know how many times you went around. You maybe some other weird thing happened that nobody told you about, right? All right, so oh, this is, I told you already, how do you prove that your program halts, right? So you have to define some measure and some exit condition. And here, let me just give you a little hint, kind of jumping off of what he'd said before. Don't confuse the exit condition with the post condition, right? People often say, well, when do you stop? Well, when I got the post condition. Yeah, but now how do you prove you're ever going to stop, right? How do you prove you're ever going to get the post condition? So don't do that, because then this part of the proof will be too hard, right? You make the exit condition be that I've made enough progress, right? You're going to have some measure of progress, and right. And that fact, what this says is here I have some measure of progress. Here's my little mile sign says how much further do I have to go? And if the mile sign gets down to 0, then we know we're going to exit, right? So I was having the progress be I that keeps getting bigger, right? But you could have your progress go up, or you could have your progress come down. Here where it's coming down, right? So you need that. And right, so here you also need that if you've exited and the loop invariant's true, then you get the post condition, right? I don't know if there's some things missing here, which we'll put in later, maybe. You have to make sure that your measure of progress goes down every iteration, right? You have to make sure that your measure of progress doesn't start off at infinity, right? All right. So this is just have a little review on this. I don't know why this comes and it goes. Right, these are all things we said, right? Loop invariant's a picture, establishing the loop invariant, right? We're going to establish the loop invariant in the minimal amount of work, right? Often I equals 0 is a good number. People good? People kind of follow this, right? In fact, what I do is when I'm designing the algorithm, I draw a picture of sort of generic top of the loop. I have some set of numbers that I know M is the maximum of, right? And then when I want to do this step, I say, oh yeah, but what do I want the loop invariant to be true when I get to the top? The first time, right? Well, that number of numbers could be 0 or 1, right? So if it's 1, I got one number and I know M's the maximum of it. So you draw that picture, right? And now you just have to write code to go from the precondition to your really simple loop invariant, right? All right. Right, you arrive at the top not knowing anything except the loop invariant's true and you haven't exited, right? And so you must make some step, right? doing this. How do you get the postcondition, right? We know we're done. Why do we know? We know the loop invariant is true because we exited, because we maintained it. We know the exit condition's true because we exited. And so from that, we just need a little extra work to get the postcondition. Right? People following this? All right. Okay, you ready for the proof that this works? Right? Those are all the pieces that we need. And when we bring one up, we'll say what the piece means. All right? So what does this say? This says if we can establish the loop invariant and we can maintain the loop invariant, then the loop invariant is always true, as long as we haven't exited, right? Everybody good with this? All right. What does this say? This says if the loop invariant is always true, and as long as the loop invariant is true, the code won't exit, and the code won't crash. The code knows how to take a step, right? If the loop invariant is true, then we're always going to take a step, right? Because there's some weird situations code could get into which will make it crash, right? But this is saying as long as the loop invariant is true, we won't crash, right? We'll always keep taking steps, right? And if we keep taking steps, and this is one that we didn't have on the earlier page, right? And every iteration we make progress, we decrease the measure of progress, then every iteration we make progress, right? This says if when the precondition is true, our measure of progress isn't infinite, and we keep making progress, then eventually the progress will come down to 0, right? Assuming that you don't do something stupid like a progress of 1 and then a half and a quarter and a 16th, right? Don't do anything like that. I mean, we're always making progress of at least 1, right? And then this says, if your progress goes down to 0, and having a progress of 0 ensures that you exit, right? Then that ensures that we exit, right? Everybody got following, right? And then we say, we know we're going to exit. We know the loop invariant is always true until we exit. We know that those two things give us the postcondition, and hence we get the postcondition, right? And so we're happy, right? Everybody good? Everybody part of this religion now? Good. Right, so let's just saying that again. Right, same idea again. Don't worry about the whole computation. Right, I think, right, this just say, right, you can't work, when you get into, if you're trying to get from here to school and you end up in a tree, then that's going to be a problem, right? So we don't want to figure out what to do no matter what, right? We want to assume that some basic things are true, right? Some basic loop invariant is true, right? And we're going to always assume that you're in this sort of safe place. And right, when you're in the middle of the computation, what do you want your algorithm, your data structure to look like? And how do what do we want our loop invariant to be? We want it to flow nicely, right? Our loop invariant is pretty close to the precondition, right? When you have one number, right? And it's pretty close to the postcondition when you have all the numbers, maximum of all the numbers, right? So a good philosophy in life is to ask for 100% of what you want, right? So you just say to your fairy godmother, I'm at the top of the loop. I want this to be true, right? And then you have to maintain it, right? No, don't assume anything that's not written in your loop invariant, right? Everybody kind of follow this? Now, on tests, I will often say, what is the loop invariant for such and such of algorithm? And these are things that you could say that will get you a mark of 0. All right? If you give me the code, that's not a loop invariant, right? Loop invariant is a picture. If you give me the precondition or the postcondition, or you give me some statement that's always true but doesn't really help us, right? If you tell me an action, right? If you tell me what does the code do each iteration, right? That's not a picture. That top line, x equals x plus 2, is it a true math statement? It's not, right? So my father, I took a course from him. He was like, you got to, computer science statements are not math, right? So that's not math. And so you want to convert it into something that is true as a math statement. And since we want to say we have 2 points in time, right? The loop invariant's true. You come around, the loop invariant's true again. All the values have changed, right? So we want to say, give some name to the values of the variables when you're at the top of the loop, right? You can use I prime, right? X is the variable, right? X prime could be the value at the top of the loop versus X double prime, the value when you come around again. Or you could use Xi and Xi plus 1, Xt plus 1. Everybody see that we have the values of the variables when we're at the top, and we have the values of the variables after you've come around again, right? Are people good? We're kind of going fast, but it's this is a little bit more than we should be teaching anyway, yeah? It's a picture, a statement that needs to be true every time you're at the top of the loop, right? And so if we define here that X prime is the values at the top of the loop, then I know the loop invariant is true for the X prime values, right? Now I want it to be true for the X double prime values, right? And when I say that I know the code happened, well, what's this? This is a math statement that shows me the relationship between the old values and the new values, right? The program x equals x plus 2, what it does is it takes the old value, adds 2, and makes a new value, right? So here, right, we know the loop invariant's true for the x prime values. We know this relationship between the x double prime and the x prime, right? So we can prove it's true for the x double prime, right?